All right, welcome everybody to the first lecture in a MISU Drought seminar series that we're doing at Stockholm University, spring of 2022. I am Professor Toby Alt. I'm from Cornell University. I'm visiting MISU this year as part of a sabbatical that is funded by the Fulbright Scholarship Program. And what I hope to do today is really just give you an overview of the main topics that we're going to cover in the next few lectures of this course. And this should give you a good taste of the scope of this course and what I consider to be the main building blocks of drought research today. So first of all, what are we talking about when we talk about drought? And if you're familiar with drought literature or drought concepts, you probably have come across the idea of different types of drought. So meteorological drought usually means drought that's occurring on timescales of weeks. This would be in the context of a place like upstate New York, where I live most of the time. And there are, a few weeks that go by in the middle of the summer, and if it doesn't rain, crops start to dry out, farmers start to get concerned. A few more weeks go by without enough rain in the summertime. It's all rain-fed agriculture, and you start to experience drought conditions, and that's usually called meteorological drought. But the important part of meteorological drought is that it tends to be relatively short timescales and related primarily to weather variations. If droughts persist for a longer period of time, we're talking now about months or seasons, so the whole summer ends up being dry, that tends to affect agricultural products and is usually termed agricultural drought. There's also a concept that's related to agricultural drought, but it refers more to what happens in natural ecosystems or ecosystems that are obviously not managed as directly as agricultural systems. And the timescales for ecological drought tend to be similar in many ways to those of agricultural drought, or sometimes a bit longer. So again, we're talking about months to seasons. And this is a picture that I took when I climbed Mount Adams, which is there in the background, with my sister in the summer of 2019. And there has been, as many of you who may have been watching the news about the Northwest or the Western US in the last few years, there have been a series of prolonged drought events resulting in huge fires. And what you're seeing there is the remnants of one of those fires a couple years later. And the trees there were severely afflicted by the drought initially, and then because they were drier, they supplied fuel for one of these raging massive fires that you see in Western North America almost every summer now recently. If droughts persist for a longer period of time, they're usually termed hydrological droughts. An agricultural drought could turn into a hydrological drought by simply enduring for another series of seasons or years. This is a picture of Lake Mead taken from an airplane, obviously. And when we think about hydrological drought, we're talking about reservoir levels, among other things, lake levels, stream flow levels. We're seeing an impact of drought on the whole hydrological system and the ability of that system to store and retain water that might be used for other purposes, both agriculture and municipal water uses alike. And recently, in the last few decades, you've seen this idea of socioeconomic drought, which is related but a little bit different in the sense that it relates to both the supply and the demand for water. So here's a picture of Los Angeles, a huge sprawling city, and as you can imagine, the water needs of this city are substantial. And as has happened in a number of places around the world, you can get into a socioeconomic drought simply by having demand for water resources that exceed the supply. So with no theoretical change in the baseline of available water, you still might get into a drought situation where the municipal water demand exceeds that of the supply from rainfall and from snowpack. And this introduces, I think, what's a really important key concept for drought. Before we get into how we monitor it, and I want to just go back one slide here to this idea of socioeconomic drought, because the key qualitative aspect of drought across all these different timescales and across all these different definitions, the key part to think about when you think about drought is that there is a deficit in the supply of moisture relative to the demand. And now supply and demand can be taken to mean a number of different things. In this case, the demand for socioeconomic drought would be by municipal water use. But in some other context, it could be the demand for water for agriculture, or the demand for water by ecosystems for trees to grow and for plants to thrive. Or the demand for water could be from just rain-fed crops to grow food. So across all these different timescales of drought, there's this core principle that applies to all of them, where there's a mismatch between how much water is being used by the system of interest and how much is being supplied. And you can even extend it to the demand for moisture from the atmosphere itself. So in the case of meteorological drought, you might have a few hot, dry days in the middle of summer in a region that tends to get plenty of rainfall in the middle of summer. And that demand for moisture now is coming from the atmosphere itself. It's accelerating evapotranspiration rates and therefore driving drought conditions because, again, the demand exceeds the supply. So with that conceptual framework in mind, how do we monitor drought? And this is really a US focused perspective right now. This happens to be the US Drought Monitor from February 3rd, 2022. This is a product that is collated from regional observers across the US who report back to the Drought Monitor on the conditions that they're observing in their county, in their region, in the field. And so it's inherently a qualitative metric of drought that then is made more quantitative by categorizing the levels of drought that are being seen in each section that's being observed, each region that's being observed. And again, this speaks to the idea that drought is inherently a qualitative phenomena. One person's drought might not necessarily be a drought to someone else. In this case, primarily is agricultural or hydrological drought in the places that you're seeing deep red and orange colors out in the west. But meteorological droughts could show up here as well after a few weeks of below average moisture or above average temperatures that could drive higher evapotranspiration rates. And again, it speaks to this concept of drought being driven by a mismatch between supply and demand for moisture. There are also a number of in situ measuring projects around the world and in the US. This happens to be a picture of one of our soil moisture sensors at the Cayuga Nature Center in Trumansburg, Tompkins County. We've got an ongoing project in collaboration with the Paleontological Research Institute and Museum of the Earth in Tompkins County to collect soil moisture measurements in real time, or close to real time, using these sensors. Measuring soil moisture directly is tricky, though, for a couple of reasons, some of which are probably fairly obvious, but I'll go through the main one, which is that if you really want to get an accurate measure of soil moisture, the only thing you can do to really directly measure soil moisture is go out and dig up a chunk of soil, weigh it, dry it out, and weigh it again. But if you do that, that's a very disruptive sampling technique. And it makes it impossible to do continuous long-term measurements of soil moisture in the same way that we make long-term measurements, continuous measurements of temperature, precipitation. So instead, what we tend to do when we measure soil moisture is we use electric magnetic techniques that would allow you to put a probe or a sensor in the soils and measure capacitance, so the resistance of the, not quite the same as resistance, but we're measuring the ability of the soils to conduct electricity. And the wetter they are, the better they conduct electricity. And the drier they are, the more they resist the flow of electricity. And that change measures the change in moisture and hence serves as a proxy for soil moisture content. But there are another few limitations one needs to be aware of when trying to measure soil moisture. First of all, as anyone who's been out in the field knows, there's a lot of heterogeneity to soil types across space. And even in this area where we're setting up these experiments, there are sandy soils and clayey soils and soils that are rich in organic material, and each of those are going to have different soil moisture holding capacities. And therefore, one site might not be representative of what's happening across a larger spatial scale. And that's different from temperature. You don't tend to get such strong gradients over small spatial scales in temperature. Another problem with soil moisture measurements, however you're trying to do them, is that especially in the summertime in many regions across the world, when you have convective precipitation, the convective precipitation events can be very localized. So maybe in Ithaca, New York, there's a rainstorm that dumps an inch of water, a substantial amount of water over a short period of time in the summer. And this happens every summer. And that in turn makes the soil moisture content right around Ithaca increase and maybe alleviates or prevents drought conditions from unfolding. But just a little ways away, let's say in Syracuse, there isn't a rainstorm on that particular day. And now the soils are significantly drier and maybe a drought starts to unfold. Even over this small spatial scale of a few dozen miles, you can get gradients in soil moisture content that arise because precipitation itself is spatially heterogeneous. And that's the key thing to be aware of when thinking about drought monitoring, as opposed to something like temperature or pressure, or what we're used to with gridded global scale climate data products. We don't have that same coherence in many cases for precipitation, and therefore we don't have it necessarily built into soil moisture. Now, a recent alternative, very exciting and important development in the last decade or so, has been the ability to do soil moisture measurements from space using remote sensing. And we'll get into that in a future lecture. But what NASA has been able to do and other satellite missions have been able to do is directly infer surface soil moisture content through remote sensing. And that is a really powerful tool because it gives you a complete spatial field all over the globe at relatively high resolution in space and time. So we're talking about weeks or months in time and a few days, in a few kilometers, 9-10 kilometers in space. So if you think about the implications there, these new satellite remote sensing global soil moisture products are completely new and unique. They're unprecedented in terms of what we've been able to do for drought monitoring. Because before this era, the only long-term measurements were ones that were in situ sensors, either using the electric soil moistures that we talked about before or some other type of direct measurement, but they lacked spatial coverage. And the only spatially complete indices of drought or indicators of drought were derived from other variables. And I'll talk about that in a second as well. So An important component of monitoring drought, given the limitations of data that we just went over, the fact that until recently we haven't been able to get spatially complete coverage in the same way that we've been able to get spatially complete coverage for temperature or uh, pressure using reanalysis. Drought literature in the last few decades has turned to some form of modeling. And in the simplest sense, the modeling has taken the form of drought indices. So here we're showing data from a project that my group has worked on, where we have computed this thing called the Palmer Drought Severity Index. So it's written there, PDSI on the right. The Palmer Drought Severity Index is a very widely used tool for measuring relative wet and dry conditions using only meteorological data as input. And that's the really important part. And the power of using something like a drought index is that you're getting away from the need to directly measure soil moisture because you're trying to estimate it using some model. And then in the case of a drought index, not only are you trying to model soil moisture, you're also trying to normalize it so that an anomaly of, say, 1 standard deviation or -1 PDSI units or -2 PDSI units means the same thing, whether it's computed from Maine or New York State or Sweden or Costa Rica or Arizona or Australia. All around the world, ostensibly, a unit of PDSI should mean the same thing so that droughts can be compared across space and through time in a uniform and consistent manner. And that's the real motivation behind using something like a drought index. Taking a step further down the path of modeling, and we'll go through all of these in more detail throughout the course of the next few lectures. We have leaky bucket models, which approximate moisture balance in the way that a leaky bucket would, in a sense. You have the inputs from precipitation and then evapotranspiration, which gets parameterized. You have some loss to the groundwater below, and you also have runoff. And so in that sense, it's a simplified moisture balance model of the surface layer. And that can be a powerful tool for monitoring or modeling drought through time, because again, it only requires meteorological input to be able to estimate soil moisture state through time. We have more sophisticated land surface models that have become a really valuable tool in the last 2 decades or so. This is a diagram from National Center for Atmospheric Research, their community land surface model, which shows the 3 main components that go into this land surface model. There are the surface energy fluxes on the left, the hydrology of the model, that's sort of what we care about, but to get the hydrology right, you have to understand something about the surface energy fluxes. And then going a step further, you can include biogeochemical cycles, because water is inextricably linked to what happens on the ground in terms of plant growth, carbon sequestration and storage, photosynthesis. Water, carbon, nitrogen, they're all coupled in their flow through the vegetated system. And so land surface models attempt to accommodate all of that. And they're used both with historical meteorological data as well as in a coupled sense with the atmospheric components or the full GCM components of the climate models that are used for climate change assessment. But they are several orders of magnitude more complex than these simpler leaky bucket models or these simpler drought indices. And because of that, they require more data, and the data quality and the types of data that you need isn't really up to the task until more recently, basically until the satellite era in most cases, which means that you can compute drought indices or leaky bucket models going back much further maybe even in this case, we've gone back to the 1950s, but you can go back, people and researchers have gone back even further than the 1950s using meteorological data to compute drought indices, and leaky bucket models have been computed all the way back into the 1950s, whereas these more sophisticated land surface models tend to only have data coverage from about year 2000, so the last 20, maybe 30 years. As long as you've got satellite data to get some of the fields for the radiative fluxes, you can use some of these land surface models. But this introduces a problem that we're going to come across again and again and again. The more data that you need, the more sophistication that you add to your model for surface soil moisture, the shorter the temporal coverage you tend to get. And so there's always going to be a trade-off. And I think if you remember nothing else from today's lecture and the next few that we're going to go through, there's always a trade-off when trying to do drought research. If you want more temporal coverage, you usually have to sacrifice spatial coverage. If you want more detail and higher spatial resolution, you often have to sacrifice temporal coverage, and so on. And so it's really about knowing which product, which tool, which approach is most appropriate for your particular research needs. We're going to get into a bit of what causes drought. Here's a picture of the ocean. Hint, hint, hint. Oceans play an important role on interannual timescales in modulating where the storm tracks go and where convective systems end up being located across the world. And because of that, they affect drought through remote teleconnections. Many of you will already be familiar with the idea that El Nino and La Nina have big interannual impacts on drought. Here's an example of this. This is a figure from a review paper in Science that I wrote a couple years ago, right at the start of the pandemic, so no one ever reads it. But you should go read it. It's I'm proud of it. I liked writing it. I hope some people out there will find it interesting and useful. And I've got a whole series of references from today's lecture at the end of this lecture. And I'll do that for most of the future lectures. I should do that for all the future lectures as well. So the Nino 3.4 region is shown in that box. It's sea surface temperature averaged for that rectangle. And then I've correlated those sea surface temperatures computed from winter, boreal winter, JFM, with the Palmer Drought Severity Index for the following summer. It's not necessarily the best way to do this, but it's a simple way to do it, and it shows really clearly some of the main areas where those El Nino teleconnections, El Nino La Nina teleconnections, end up being seen across the globe. So we'll get into some of the process and the dynamics, the atmospheric dynamics that link variations in sea surface temperature to drought impacts on land. And we're going to use the concept of the atmosphere as a dynamic fluid that transports moisture around. And it's the anomalies or the aberrations in that flow of moisture that lead to droughts, and of course lead to pluvials as well. But we're going to focus on droughts and the role of the atmosphere and the role of the oceans in shaping the flow of the atmosphere to give rise to droughts. And we're going to look at drought and climate models. There are a whole slew of interesting new complexities and problems that we have to consider when transitioning from observational versions of drought, observational constraints on drought, to model constraints, and not the least of which is that models tend to have biases in their precipitation fields, among others. And so a drought in a model in a given region might actually be, it might be a drought for that model because it's an anomaly that you see, but the mean precipitation field might be higher than in observations, in which case the impacts might look a little bit different in the model. And we'll get into how that plays out specifically in a future lecture. But if you're only going to watch this lecture, be aware that translating our drought indices and our soil moisture models from observations to climate models is not a trivial feat and has been a theme in the literature that is not fully resolved even today after several decades of research. So here's an example of how this might play out and how you need to be aware of it. On the top, we just have the precipitation trends over 21st century. And those of you who are used to looking at CMIP5, or this happens to be from the CESM large ensemble, but if you've seen CMIP5 data, you're familiar with this picture, CMIP6, where in general, wet areas get wetter, dry areas get drier. There's also a number of places where there are negative trends in precipitation, Central America that are wet regions to begin with. And if you only focused on the top map there, you might come to a conclusion about water availability that's different from what happens when you look at soil moisture. So in the bottom, we have the same basic analysis. We're just looking at trends, but using June, July, August soil moisture instead of precipitation. And now places like, especially Central America, the US Southwest, most of Mexico, parts of Alaska, much of South America, you see that there are negative trends in soil moisture, even though the precipitation trend is positive. And a more clear example of that is, again, from the CSM large ensemble experiment. Up on the top in the blue shading, you have the full ensemble through time, which towards the end of the 21st century sees an increase in precipitation total and also the extreme heavy rainfall events. And so if you only considered precipitation, you might conclude that there would be very little change or maybe a slight increase by the end of the century. But if you look at soil moisture, the opposite trend is present. And this responds to the role of higher temperatures driving increased evapotranspiration during the summer months. And so one of the things that you need to be aware of if you're looking at soil moisture or precipitation projections in climate models is that they don't, after a certain point, they don't necessarily agree with each other. That precipitation alone is not necessarily a proxy for what's happening in soil moisture because the role of evapotranspiration in a warmer climate might change. Now, adding even more complexity to this, and we'll get into it, is the role of CO2, quote unquote, fertilization, or the idea that under a higher CO2 world, plants are going to be able to make more efficient use of water because they'll have more CO2 in the atmosphere, so they don't need to release as much water. They need to use as much water to do the same amount of photosynthesis. Now, that effect is ostensibly included in this particular model, and even with that effect included, you still see a net decrease in soil moisture over time, even though precipitation and CO2 are increasing. Another big open-ended problem that I think is important and interesting, and we will spend a little bit of time on towards the end of the semester, is the role of tropical decadal variability. So we know that El Nino has an impact on drought in Western North America and throughout much of the globe. But what we don't fully understand in the tropical Pacific is how important or how high amplitude is decadal variability. So up in the left there, I've just shown it in the observations. Decadal variability is about 10% of the total variance. And if you go across the models, these are all the models from CMIP5. You can look in the index in the paper for which ones they are. There's two things going on that I want to draw your attention to. The radius of the circle is proportional to the variance of the models. So some of the models have higher ENSO variance, some of them have lower ENSO variance. The black circle in each of them is the observations for reference. The other important part to notice here is that wedge, little pie piece in the upper left in each of these models, depicts the fraction of their variance that's occurring on decadal timescales. And it's not the same from one model to the next. And so this is important because we think that if there's a strong teleconnection between the tropical Pacific and hydroclimate throughout the world, and the amplitude of decadal variability is different from one model to the next and differs from the observations, then there are uncertainties in our estimates of decade scale drought risk emanating from tropical decadal variability. And this is an unanswered open problem that continues to receive attention in the literature and is an important one to be aware of and to think about, especially in a climate change context. All right, I'll wrap up here with my own thoughts on timeline of developments in drought research, and hopefully give you some ideas of where you might want to take your own research goals. I've organized this by sort of the technology in recent decades that has promoted developments in drought research. So in the 1990s, started to have every university and most individuals started to have their own desktops and laptops. That made it a lot easier to compute drought indices and simple leaky bucket models of soil moisture. You didn't need a supercomputer for these things. By the time we reached the early 2000s, supercomputing resources had become pretty ubiquitous across research universities and government labs, government facilities across the country, across the world. And that paved the way for some important advancements in land surface models, which are sufficiently sophisticated and they have global scale at 1 degree resolution that in most cases you wouldn't want to be using a desktop or a laptop for that. You would want to use a high performance computing system. And so we also in that era saw the emergence of these new land data assimilation products, and I alluded to those earlier. These are more sophisticated land surface models that are driven or forced by meteorological boundary conditions to try to estimate soil moisture through time. In the 2010s, we had this NASA mission that I alluded to, the SMAP, as well as a few others that for the first time started to provide global coverage from remote sensing of soil moisture in the surface layer. And finally, here we are in the 2020s, and some tools that seem to be popular and important and significant for drought research include the machine learning, AI fields that have just exploded in the last few years. There's also low-cost sensors, like the project that we're doing with the Museum of the Earth in Tompkins County, where we've got low-cost sensors out in the field doing real-time measurements and broadcasting that data back through a LoRaWAN network to a cloud server where we're able to monitor and track variations in soil moisture level through time. So I imagine those of you who are doing research, you're aware of those tools, and they will lead to the new exciting developments in drought research this decade. I'll conclude here. If you want to jot these down or pause the video and find these papers, these are a few recommended readings. These are all review papers to give you an overview of some of the drought concepts that I've talked about here and the technologies and the tools that we use to try to understand drought. All right. Thank you very much.